want to solve the non-homogeneous second-order linear constant coefficient differential equation y double prime plus y equals t squared. Now, the homogeneous version of the differential equation is just y double prime plus y equals 0. We've seen the solution before. We know that a fundamental set of solutions consists of y1 equals cosine t and y2 equals sine t. That's a fundamental set of solutions. So the general solution to the homogeneous is just the set of linear combinations of sine t and cosine t. Now, what should we guess for our particular solution to the non-homogeneous equation? Well, here we have t squared. So you might think just guess a constant times t squared. Y would then be a constant times t squared, but then when we take y prime, it'll be a constant times t, and y double prime will just be a constant. So the general rule is this: when you have a polynomial that's nth degree here, the y term will similarly be an nth degree polynomial, but you'll have smaller degree polynomials for y prime and y double prime, n minus first degree and n minus second degree. So what we want to do is actually take a general nth degree polynomial here, in this case a general second degree polynomial. So we'll try y of t is at squared plus bt plus c. Then it's easy to compute y prime of t is 2at plus b, y double prime of t equals 2a, so that y double prime plus y is just this plus this. That would be at squared plus bt plus, we'd have c plus 2a. And we need this to equal t squared. Here we have second degree polynomials here and here, so we just want the coefficients to match. Well, the coefficient on t squared is a here and 1 here, so we need a to be 1. The b is the coefficient on t, which is 0 here, so b has to be 0, and c plus 2a is the constant term here, and 0 is the constant term here. So technically what we need to do is solve this system of 3 equations and 3 unknowns, but it's a very simple system to solve. A is 1, b is 0, and then one can see really quickly that c has to be minus 2, since a is 1 and c plus 2a is 0. In other words, y of t has to be 1 times t squared plus 0 times t minus 2. And remember, you should always be checking these. So once you've done all this, check real simply that t squared minus 2 is a solution to y double prime plus y equals t squared. You can probably check that in your head, and you'll see that that works. What is the general solution to the non-homogeneous? It would be y equals c1 cosine t plus c2 sine t plus t squared minus 2. And remember again, c1 and c2 can be any real numbers. Let's look at another example. You might think this example is just like one we've seen before, and it's very similar. Let's look at the homogeneous equation. Y double prime minus y equals 0, and we've solved this one before. It has a fundamental set of solutions. y1 equals e to the t, and y2 equals e to the minus t. Now, what should we try for our non-homogeneous? Well, it looked like before we want to try a constant times e to the t. But here, let's see where that will actually be a problem. If I try using y as a constant times e to the t, that will already be a solution to the homogeneous equation, so that the left side will actually always end up being identically 0. And no matter what choice of a we make, because any multiple of e to the t is a solution to the homogeneous equation, and thus we'll never be able to match what we have on the right. We can refer to this in many ways. I would call it interference from a solution to the homogeneous equation with what we would otherwise guess for a solution to the non-homogeneous equation. So I'll write we would try y of t equals a e to the t, but there's interference from the homogeneous equation. If you remember from all the earlier examples, there was no such interference. The thing that we used to try to find a solution to the non-homogeneous equation was not a solution to our homogeneous equation, and everything worked out fine. So here's the question: what do we do when we have such interference? The general rule of thumb is the following. Just multiply everything by t. So we'll try y of t is, instead of e to the t, we'll try t e to the t, and of course we'll put some constant a here, which is our undetermined coefficient, and try to see if we can find a that makes that work. Well, let's see if this does work. What will y prime of t be? Using the product rule, it's the derivative of the first times the second. That's a e to the t plus a t e to the t. And I will compute y double prime of t. That's just a e to the t. That's the derivative of this piece. And then the derivative of the second piece is just what we had before. We have another a e to the t plus a t e to the t. That's 2a e to the t plus a t e to the t. If we look at y double prime minus y, we get this minus this. The a t e to the t parts cancel, and we get exactly 2a e to the t, and we need this to equal just e to the t, so it's pretty clear here a is 1/2, and y of t will be exactly 1/2 t e to the t. This will be a particular solution to our non-homogeneous equation. Again, check that. Every time we compute these things, I want you to check these results. You can pause the video now and check the result. Now, what's our general solution to this non-homogeneous differential equation? It's y of t is c1 e to the t plus c2 e to the minus t. That's the general solution to the homogeneous equation, plus our particular solution, 1/2 t e to the t. And this works for arbitrary real numbers c1 and c2. Let's look at one more example. Again, this is familiar but slightly different from our earlier examples. Here, for the homogeneous equation, y double prime plus y equals 0, we had a fundamental set of solutions. Y1 equals cosine t, and y2 equals sine t. And immediately you can see there's going to be interference here, because if I tried to just use a constant times cosine t plus a constant times sine t as my guess, the left side would always be 0. Those are exactly the solutions to the homogeneous equation. So that won't work for our method of undetermined coefficients for our guess for a particular solution to the non-homogeneous equation. So what are we going to do? Again, we'll bump things up by a factor of t. We'll try y of t, And remember, the general thing we would try would be a cosine t plus b sine t. So I'll have to try a t cosine t plus b t sine t. And you'll see why we really do need both of those terms. Now we have to just compute what's y prime of t. Again, using the product rule frequently here, we'll get the derivative of at, which is just a cosine t, and then at times minus sine t, so we'll get minus at sine t plus b sine t plus bt cosine t. We'll compute y double prime. That's just going to be minus a sine t, and then we're going to have minus a sine t again. And then there's the product rule. That's the derivative of the first times the second is here. The first times the derivative of the second will give us minus at cosine t. And then we'll just keep doing a similar thing over here. We'll have b cosine t plus we'll have b sine t, and then we'll have minus bt sine t. So that here y double prime. Sorry, that's messy. Let's get rid of that. Y double prime plus y. When we take this stuff here, y double prime, and we add y, you'll see that the at cosine t cancels the at cosine t there, and the bt sine t cancels the bt sine t there, which is vital if we're going to be left with just cosine t. And what we have is, here we have minus to a sine t, and then we get, well, this should have been cosine t here. That should have been cosine t. And then we have plus 2b cosine t, and this must equal cosine t. So the a has to be 0, and the b has to be 1/2. In other words, y of t must be exactly 1/2 t sine t. And our general solution, and you should again check all of these, is, where is it? Y equals c1 cosine t plus c2 sine t plus 1/2 t sine t. Now, this method of undetermined coefficients, we've been applying it only in the case of second order linear constant coefficient differential equations in order to find a particular solution to the non-homogeneous equation. In this case of second order linear constant coefficient differential equations, what we use as our guess depends a lot on the form of the function on the right side of the equation. And there are many different possibilities. In the book, in section 3.5, there's this table, which I copied from the book, but you have it as a reference in your own textbook. And this tells you, if you see g of t of any one of these forms, it tells you what to guess for your y of t. So I would say memorize this table. This table tries to present everything in great generality. So if you just look at many different examples that are related to these, I think you'll find this pretty easy to come to grips with all the different things that can happen.